Let me welcome you on behalf of all ACES Fellows and behalf of all IRTG on Modern Inverse Problems Fellows to the 19th Charlemagne Distinguished Lecture Series by the presence of Vice Rector Professor Matthias Wessling. My name is Violeta Karyophili. I'm a doctoral candidate at CATS. Together with my colleagues Vera Löser and Aravind Sankanar, and with support from numerous sources throughout ACES, we have had the great pleasure of coordinating this semester's CDLS. I also want to express our gratitude towards the former ACES Fellows, our current colleagues, the senior research staff, the service team, our advisors, for making this event today, for making our education at the ACES and IRTG Graduate School possible. We are also honored by the Vice Rector Professor Matthias Wessling for supporting this event. Finally, we are thankful to be students of a renowned university such as RWTH Aachen University. It turned 150 years old 9 days ago. It was Monday, October 10th, 1870, when a group of young people like us was the first to attend Aachen's Polytechnic Königliche Rheinisch-Westfälische Polytechnische Schule zu Aachen. The CDLS is a student initiative started in 2010 by the Fellows of ACES. It now takes place for the 19th time. Every semester, the ACES Graduate Schools Fellows and the IRTG MIP Fellows have the great opportunity to invite a distinguished guest to learn from their experience and character. First, I would like to introduce Professor Matthias Wessling. He is the Vice Rector of RWTH Aachen University.
Do you want me to speak the address now?
Yes, please.
Very nice. Thank you very much. So I think I'm probably the least important in this audience, but still I would like to convey the gratitude of the rectorate that you have organized this 19th Charlemagne Distinguished Lecture Series. It's an honor to have the lecturer, Professor Karniadakis, with us today. The rector himself cannot be part of this because he is in a well-deserved holiday this week. He didn't have any holidays for the summer because he had a serious injury and worked through the summer. So this is the first time that he can escape, and I think that's indeed very well deserved. The CDLS looks back on an impressive history, all the way going back to 2010. As the Vice Rector for Research, I usually look at big pictures, but I must say I've been looking with more detail into the publication record of the candidate today and the lecturate of today, and I'm very impressed, I must say. And I think the graduate students of the IRTG should absorb every single word he's going to say. And every time ICES and the International IRTG on modern inverse problems is gathering, I think this is an exciting event, and I'm extremely pleased to address you today. The initiatives that you're developing provides excellent education to doctoral students and cutting-edge research. It's at the crossroads of different disciplines: mathematics, computer science, mechanical engineering, flow engineering, and that is at the heart of RWTH Aachen, operating, doing research at crossroads of disciplines. So we are an integrated interdisciplinary technical university. It's a mouthful of words. It's integrated, it's interdisciplinary. Integrated, it means different faculties cooperate together. Faculty 1, mathematics, for instance, with mechanical engineering. ICES is part of that, and the Center for Simulation Science is an expression of that interdisciplinarity. We are a technical university, which means that we also try to have a lot of impact in what we are trying to do. And what we want to impact in particular is global challenges, offer solutions, in particular with respect to sustainability for future generations, which means this is the generations of the students that are gathering here today. Very important. And I think The universities, may it be in Austin, may it be at Brown, may it be in Aachen, they are actually trying to prepare the next generation's researchers to tackle those global challenges. To be excellent in our research and teaching, we need experienced researchers and we need young academics as well. But we also need lighthouses, and I think one of the lighthouses we have invited today. And we're very proud to have this lighthouse present with us. What I really appreciate about the Charlemagne Distinguished Lectures is therefore that the doctoral students themselves organize this. So a university, we organize, especially as the rectorate, we only can organize boundary conditions. Within the boundary conditions, we need entrepreneurship, we need active students, we need members of the body of the university that explore what we can offer. And we try to organize that as good as possible with the aim to really address important progress for sustainability in society. So you learn so much by doing all of this, and it's a really great success that you have initiated this long time ago, the CDLS, and that you still continue that. And I'm very pleased that we have Professor Karniadakis today with us as being an extraordinary scientist. If you look at his Google Scholar profile, you will exactly know what that means. And the amount of work, the depth of the work, the impact he has been having on others is tremendous. And I'm sure that he will also impact your being a member of the IRDG. Even though face-to-face encounters are today not possible, I'm convinced that with the technical tools that we have today, that we can organize something very special. That the organizers provide room, a digital room, but at least it is room for scientific discussions and personal networking. I can only encourage you to use this afternoon or any other moment within the IRTG to network. Network is probably one of the most important assets that you can develop. Sitting alone in your office is one thing to solve the daily challenges that you have, but doing that in reflection with others and doing that with others in teams is even more important. So this CDLS and everything around it should offer that room to you. I would can only wish you a wonderful afternoon. I can only thank Professor Karniadakis for his contributions to this afternoon, and I hope you have a wonderful time together. Thank you very much.
Thank you, Professor Wessling. Next, I would like to introduce Professor Marek Baer. He is the head of the Chair for Computation and Analysis of Technical Systems, CATS, in the Faculty of Mechanical Engineering of the RWTH Aachen University since 2004.
So thank you, Violetta. I hope that everyone can hear me okay. Thanks, first of all, Matthias, for the introduction. Thank you, Aravind and Vera, for the organization. I will just say a few words about the whole series and about George, I guess. So it's almost to the day today that 10 years ago, we had the first Charlemagne lecture event in Aachen, where Peter Lex was invited and gave the inaugural talk. Since then, as it was said, every semester, we invite a distinguished speaker, invited and hosted by the fellows of the what is now School for Simulation and Data Science, which includes ACES, IRTG, and also HDSLE, and a few other programs. I must say that this is probably the most attended lecture so far, with almost 150 participants in the Zoom right now. So that makes me, in fact, very happy. And having George Karniadakis with us today is also a great pleasure. I think we first met George maybe 10 years ago at various blood modeling workshops. George's work on HPC approach to blood simulation with individual cells being resolved by the computation was really a fantastic contribution in those days. And now he, of course, moved to many other exciting topics like stochastic PDEs that we will hear about today. I don't know if you remember this, George, but we wrote at some point an NSF exascale proposal together, which went through the first phase of the evaluation, it was a very competitive program, did not get to the second round. Later, I figured out that everybody in that group of PIs, large group, was actually Greek or had Greek roots. Only myself, I was not. Maybe I was the weak link, and I'm sorry about that. But now I'll just turn it over to Violeta Karyophili, who is Greek and who will introduce you a little bit further. Thank you very much.
Thank you, Professor Baird, for this personal account. As part of CDLS, we, the students, choose someone who inspires us. We choose someone who inspires us through their numerous contributions to research, their achievements throughout their career, and the enormous impact they have had on our joint field of computational engineering science. Today, I have the honor of introducing to you as the 19th CDLS speaker, Professor George Karniadakis. Professor Karniadakis started his career in Greece with a diploma in mechanical engineering and naval architecture at the National Technical University of Athens. He followed this with his graduate studies, completing a master's in mechanical engineering and then a Ph.D. in mechanical engineering and applied mathematics at MIT in 1987. He was appointed lecturer in the Department of Mechanical Engineering at MIT in 1987, and subsequently he joined the Center for Turbulence Research at Stanford, NASA Ames. He joined Princeton University as assistant professor in the Department of Mechanical and Aerospace Engineering and as associate faculty in the program of Applied and Computational Mathematics. He was a visiting professor at Caltech in 1993 in the Aeronautics Department. He joined Brown University as associate professor of Applied Mathematics in the Center for Fluid Mechanics in 1994. He became a full professor in 1996. He has been a visiting professor and senior lecturer of ocean mechanical engineering at MIT since 2000. He was a visiting professor at Peking University, fall 2007 and 2013. He is a Charles Pitts Robinson and John Palmer Barstow Professor of Applied Mathematics at Brown University since 2013. His H index is 103, and he has been cited more than 51,500 times. Professor Karniadakis' current research interests are on machine learning for scientific computing. His broad research interests focus on stochastic multi-scale mathematics and modeling of physical and biological systems. Current thrusts include probabilistic numerics, stochastic simulation in the context of uncertainty quantification and beyond, fractional PDEs, and multi-scale modeling of complex systems, for example, the brain. In light of this, admittedly brief overview of his career and research, I entrust it now to him to tell you about his work in person. Please join me in a giving warm welcome to Professor George Karniadakis.
Thank you, Violeta. Thank you, everyone, for this generous introduction. I am very happy to give this lecture. In fact, as soon as I got this invitation, I immediately responded because I really connect with the students, I think. I see now a lot of other universities, Duke University, Emory University, the University of Toronto, at similar organizations, and they wanted me to be their first speaker because I think I connect somehow with the students, and I enjoy that very much. I give lots of lectures, but this is special. I don't know if you can see my screen.
Yes,
yep.
We can.
Except it's frozen, so I don't know what to do now. Maybe I can stop share. Okay, let's try again. Okay. Let me share.
By the way, to the audience, if you have any questions, please type it in the chat window so that during the Q&A, I will read it out.
Something happened. We had it before, and
we were able to see your screen.
Before you shared in a non-full screen mode, and then you switched to the full screen mode.
Yeah, exactly. That's what I'm trying to do. And I do that every day as something happens. Let me just tweet properly. Sorry about this delay. All prepared. Can you see it now?
Yes.
Okay, great. So I changed slightly the title to be more descriptive. And also I wanted to start with this ultimate inverse problem that is of great interest to me every morning. In fact, I just had 3 espressos. And this is some work that I did recently with LaVision, a German company from Göttingen. And the question I have here is, given this Schlieren photography, this Schlieren video, can you have any computational tools to extract the velocity and the pressure field? In fact, I was interested to know what is the maximum velocity of in this flow field so that I can appreciate and quantify the aroma of the coffee. It doesn't sound very engineering question, but it's the ultimate inverse problem because I don't know the boundary conditions. I don't know anything else. I just have a video of this 3D tomographic Schlieren video. I will tell you a little more about this, but this is the first problem I want to pose. I know you're all interested in inverse problems. I have set up a few for you. This is another one. This is a paper we published in February in Science, and we posed this type of questions of ill-posed inverse problems. For example, can we compute the body forces based on flow visualization? For example, here you see streak lines that flow around a cylinder, the well-known von Karman street. Can you actually evaluate just from this information? No boundary conditions, no domains, no Reynolds number, no velocity. Can you evaluate the forces on the body? Clearly, a problem that you cannot solve with current technologies. Okay, so let me just go to mechanics. Here we're looking at a specimen that may or may not have a few holes, like could be voids, inclusions. We may not know exactly the material properties of the inclusion, but we have some measurements in where you see these red spots, these red crosses here, for example, and that would be only boundary displacements. I don't have any stress or strain. I know that the material is hyperelastic, for example. Can I find where the hole is, how big it is, and how many holes, and so on? Okay, so before, this is some of the questions that I have in mind. As we go through the lecture, I will pose some more questions. But for the benefit of everyone here, I will start with the glossary 101, just in the way of introduction. What we mean by supervised learning in machine learning, in neural networks, is that we have lots of data, we have lots of labels. For every x space t time, I have f of x comma t. So if you have that, then you can set up the network, you can find the weights, the bias, and so on. Now, on supervised learning, you don't have any labels at all. You may have PDEs, for example. That's what I will talk about. So that could be supervised learning or semi-supervised learning. There are other types of learning. The hottest right now is self-supervised learning. I will not talk about that. But I will talk about, to start with, I will talk about reinforcement learning, which you may think is a new concept, but goes back to 50 years. Bellman, actually, this relates to the Bellman algorithm. It's a fixed point algorithm. I teach it to undergraduates. It's a very smart idea. And basically, it's this iterative process, this iterative loop where there is a policy gradient that you set up based on some objectives that you, multi-objectives that you may set up. For example, here you want to go through this maze, but you need some reward for it, and that's the cheese here. So there's a reward, there's an action, there's an observation, and all this. And this is actually very appropriate for many problems in mechanics. And I want to show you not a simulation, the type of stuff that I usually do, but an experiment I did with my colleagues at MIT. And this was an old case. This is similar to the vortex street I showed you before. But in the late 70s, Professor Srinivasan at Yale University, a student who is now a professor in Minnesota, set up this problem where they set little cylinders here, and they try to spin them to alter the wake of the cylinder so that they can reduce the drag and the lift on the body. Okay, this is a flow control application. Now, in a situation like this, the current paradigm is we really spend a lot of time to do experiments to understand what we have, the flow, the mechanism, and so on, and then we try to control it. We did here a brute force approach. We use reinforcement learning to learn directly brute force a control strategy. Then we use simulation, which turns out in this case to be much more expensive than the experiment, to understand what happens. So we reverse the paradigm. As I said, the classical paradigm is you first understand, then you control. In fact, it took about 15 years of research to fully understand the different regimes and so on. There's still currently papers written on this from fluid mechanics people. But I want to show you something else. So I will show you, so you can see here the apparatus. There is a cylinder, there is small cylinders and so on. There's all this wiring because we want to dial in the reinforcement learning algorithm and do it fast, control noise through Kalman filtering and so on. So we did this in what we call the MIT Intelligent Towing Tank. We wrote a paper last year. I was responsible for endowing this towing tank with active learning and how, and in fact, in this setup, we did 100,000 experiments in 6 months of vortex-induced vibration, something that a typical MIT student would take about 5 years to do 600 experiments. This intelligent towing tank did 100,000 experiments on its own, dialing its own frequencies, amplitudes, and so on, based on active learning. So things are there to accelerate discovery of science, and this is one I want to show you here as a first example. So I show you first the simulation at Reynolds number 500 to show how it works. After a few iterations, you can see here, the agent will learn the algorithm just about now, if you see the dot, and then it will start act. The action is on the right, on the bottom. So basically, the action is to turn counterwise the upper and clockwise the lower cylinders, so that it will destroy this vortex street and reduce the drag. As you can see, almost zero drag on the main cylinder. This is, of course, drag on the small cylinders. The lift is not there yet, but eventually we'll also make the lift zero, as you can see, with enough learning. So this, as I said, this actually took place after we did the experiment. The experiment itself, which I show you here, this is now Reynolds number 10,000. The wake is already turbulent, the boundary layer is laminar, but it takes about 10 episodes, as you can see here, to actually get to the steady state. 10 episodes will be about 15 minutes of runs, or faster, but with all the delays, we let 2 minutes in between, so the water settles and so on, but about 15 minutes. So in 15 minutes, the agent learns what people try to learn up after 15 years. So that's a kind of brute force approach. You can see that it works right away. It's a stable process and so on. Now, we don't have the physics yet. So after we realize what the mechanism is, we can go and launch a very expensive simulation for this Reynolds number regime. It took a few weeks to do this, but we realized that at high Reynolds number, the strategy may be the same, but the mechanism, the physical mechanism is different. For example, before we destroy the vortex state here, the cylinder spinning created a small scale turbulence, as you can see, so that you have a mixing of the boundary layer and the separation point moves downstream, so you get this drag reduction, as you can see here. So this is a case of finding a mechanism, accelerating a control strategy, which is very important, as you can understand, in many systems, not just in fluid mechanics. It could be done perhaps with adaptive controls, but this is a proof of concept. The first, I think, experimental proof of concept, because there's so many things that can go wrong. Here, you have to worry about the latency with the hardware. You have to worry about noise. But at the end, it takes 15 minutes to discover something. And then, of course, it will take much longer to understand it. But overall, you accelerate discovery. And that's all about. Let me move to glossary 102. Now, these are stuff that I will talk about specifically here. Physics-informed neural networks, how we can integrate data and conservation laws. We have in engineering, in all branches of engineering. I will talk about something new that is not very common in machine learning right now, how to approximate functionals and operators. So DPFnet and DPONet. These are very, very useful for engineering, for design, for autonomy, especially for autonomy, but also for design and to create surrogates in high dimensional spaces. There's also this network, if I have time, I hope I have time to show you this sweet network, DeepMNM net, because it's a neural network that we developed with DARPA funding currently. How you put DeepNets as building blocks, as Lego type building blocks to model systems of systems. And you may have heard digital twins and this type of technology that is now very trendy in engineering, in computational engineering, and beyond, in fact. So I'm going to show you not too much math, not too many theorems, just 3 theorems. This is the first one. This is, of course, the cornerstone of machine learning, of neural networks approximation. It's the theorem by George Saipenko, who was a professor, assistant professor at the time at Tufts University, not far from my house here in Boston, I live. And basically, it says that a single neural network, at that time in the 90s, we didn't have deep neural networks. Just one hidden layer is sufficient to approximate any continuous function with arbitrarily close to, with very, very small error. Now, this here looks like a series expansion where this is a monomial, yx plus theta. Yj's are the weights, theta j's are the biases. These are the unknown coefficients here. Sigma will be a nonlinear function. At that time, they were using the sigmoid. Today, we use a hyperbolic tangent, very similar, or we can use the ReLU, or we can use a sine. But the point is that this expansion now is nonlinear expansion. The theorem basically says that sigma should not be a polynomial. So polynomial expansions would not be appropriate here, for example. So since then, the theory has also been extended to discontinuous functions. There's a lot of work and I have some reference here. So last year, we had about 100,000 papers published on neural networks. More than 1,000 papers even now per week. All these use this type of approximation. I want to contrast this with two theorems that I will present later on approximation of functionals and approximation of operators, because that will give us generalization, robustness, and different levels of abstractions, which are very important, I think, for learning. Okay, so how do we learn this function? What do we mean? Well, here I have a fabricated function. I assume that I have lots of points, these red points, and then the Fourier spectrum of the function as we learn it through the network, two layers, only 20 neurons. You can see that we're learning the function very, very accurately. In fact, it does have a flavor of Fourier series where we learn from low frequencies to high frequencies. However, we also learn the discontinuity, something that we cannot do it. We learn it adaptively. And this long tail that you see now is because you can see we start right away. This is the first pass in learning. We learn the discontinuity first, roughly. We learn the low frequencies and then the high frequencies. And you can watch the spectrum on the right if you can see the movie. And then we learn this function very accurately. Now, as you can see, I need a lot of red points in order to determine this function accurately. If I was to do a scientific experiment, I don't have that many points, and I don't have the points where I want. So in many cases, in science and engineering, in the most important problems that we have very few points. So imagine you're trying to reconstruct or to discover a signal from these red points. Basically, sparse data. We're not talking about big data. We're talking about small data here. So how can I discover a solution like that to my problem? Because it's below the Nyquist frequency, for example. How can you do that? Well, let's say you have some model, or you have somebody gives you data. And the data looks like on the right panel, as you can see here, the blue points. Okay, so we have the red points, which are the real data, and have the blue points, which are low fidelity, not high fidelity. As you can see, these are very tricky points because every other period, the points are correct. Every other period, the next period, they are anti-correlated with the black line that I'm trying to discover. We call this adversarial data. So somebody gave me data, but this person was an adversary. You can imagine that in military and other applications, in industry and so on, this could be a case. Or it could be a model. The blue data could come from a computational model or physical model that is sometimes is right, sometimes is not right. Can I use this data to discover the black line, the solution? Okay, so this motivates us because there are lots of cases of multi-fidelity data. Now, this is a case of multi-fidelity data, gold data, bronze data, silver data, but also adversarial data. So we wrote this paper, which is now very popular, how you can use neural networks, which take low fidelity data here. They produce a low fidelity, an approximation of the low fidelity data of the function. Then we feed a high fidelity network, and we write this as a high fidelity, YH, is a correlation, a nonlinear correlation of the low fidelity data plus a bias. This is sort of an autoregressive scheme that is used in Bayesian statistics, multi-fidelity for Gaussian fields, but here, this like kriging, for example, that you physicists have discovered in the 70s, and co-kriging in particular, but their correlations are linear. I'm talking about here non-linear correlation. So what this composite neural network does, it discovers the capital F function, the correlation between high fidelity and low fidelity. So then I can utilize all the data from all levels of fidelity, and I can upscale it to a high fidelity. This is just a data reconstruction, so you can see the mean square errors, and the objective functions that I minimize are basically data. Now, if I do that, so this is a summary of what I just told you. This is the data high fidelity. This is fabricated functions that you can see the low fidelity, YL, YH, the high fidelity. Now, if I were just to use the high fidelity data, I would get a red dot, a dotted line reconstruction to my signal, which is erroneous, as you can see. These are my data multi-fidelity. If I use now the red data, the high fidelity, plus the blue data, the low fidelity adversarial data, you can see here, I can reconstruct my function very accurately. And the reason is because I discover through the neural network this correlation between low fidelity data and high fidelity data. This is a function, as you can see here, it looks like a parabola. It's basically this function here that correlates the high fidelity and low fidelity. So I discovered very accurately using, of course, I didn't know this function and just discovered it. So it's not trivial, it's a nonlinear correlation. Of course, this is just an example. How can you bring this to real life? How can you bring this to engineering? We just published a paper with Subra Suresh, who used to be a dean of engineering at MIT. He's now president in Singapore of a university there. But we apply this to 3D printed materials. It turns out Subra Suresh is one of the world's experts on this classically inverse problem, namely nano-indentation. How you use an indenter like this, a hard tip like that you press down on a material, and from the indentation, you solve the inverse problem. It's a nilpoise problem. Sometimes you may need more than one indenter to find the yield stress and the modules of elasticity. That technology exists since the 80s. It's well understood now. In fact, it's very accurate, down to a few percent of accuracy in terms of the yield stress, for example, which is difficult to predict. However, 3D printed materials are processed differently, layer by layer, so their microstructure is very different. That affects the bulk properties, including the yield stress. So when we apply the state of the art to infer the yield stress, we found an error, as you can see here on the right panel, B, 120%. Okay, so what we did, we used this multi-fidelity approach because we don't have enough data. You never have enough 3D data for printed materials. So you have, let's say, 10 measurements of titanium alloys and nickel alloys. And what we did, we improvised. So here is a ResNet network, just like I showed you before, low fidelity. For low fidelity, we use a lot of finite element simulations. We had a patient student running a lot of simulations, and then we use the high fidelity data as the real data, the few measurements. And when we combine it the way I show you, we went down to a 4% error in predicting the yield stress. We just filed a patent about it because we think it's very useful. And as you can appreciate, 3D print materials are extremely important for engineering and biomedicine, hard materials and soft materials. Let me pause here and ask Aravind if you can hear me, if you can see my slides, if all this makes sense. Okay.
Yes.
Thank you very much. I'll make another stop, or you can send me something on the chat if we lose connection. So in this next segment, I want to talk about how we already said that we never have enough data. In fact, I was visiting the Army Research Lab when one of the Army researchers told me that they never have big data. They never have this picture like this here, where they have lots of data. Their data, they said, is dinky, which means small, dirty, which means noisy, dynamic, which means streaming data, deceptive, he said, because the Russians are always there. I don't mean to say Russian, but that's what he said. So the enemy, they meant, is always there. So there's a possibility for deceptive adversarial data. So this is the 5D law of data. But we know that we have physics. We have physics, we have mass conservation, we have energy conservation, we have momentum conservation, we have a lot of other PDEs and other prior knowledge that we want to use. So I have here 3 cartoons. You can start from the left. This is what we probably teach in classrooms, where we assume that we know all the physics, and then we need some data for the boundary or initial conditions or the constitutive laws. But usually, most of the cases, the picture in real applications is what we have in the middle. We know some of the physics, but we don't know all the physics. For example, if you have combustion, if you have cascades of scales or cascades of reactions, reactive transport, for example, in combustion or in coagulation, in biomedicine, you never know all the small scale, fast chemistry, non-equilibrium chemistry, all the reactions. You may know advection, diffusion, and so on. And so you need data to improvise. But even in problems like turbulence, where you may know exactly the Navier-Stokes equation, is simple isothermal turbulence. However, you cannot solve it at higher Reynolds numbers, it's geophysical turbulence, because the small scales cannot be captured even with the exaflop computers. So I will be looking at this picture in the remaining of my talk. This picture on the right is also very interesting. Social dynamics, we are in social dynamics somewhere like here, where we were in physics 200 years ago, where we have lots of data, but we don't have any laws to govern that. But I think in maybe a couple of decades, we will be there too. But so today I will talk about how we combine data and physics. And this brings me to this paper that we first wrote several years ago. And I have a message here for the students. Our paper was rejected many, many times. This paper now is very popular. It's a paper that combines data and neural networks and physical laws. As you can see, it's the most downloaded paper. It has more than close to 800 citations in just 1 year. But I want to say something, not to brag about this paper, is because I want to tell the students that don't be discouraged when you have something new and your paper is rejected. Recently, I gave a talk to NSF, and I thanked National Science Foundation. I said, I want to thank National Science Foundation because every time they reject my proposal, I get upset and then I go and write a paper in science. and it's true. There's sometimes when you say new things, people will be very, very conservative. They don't want to hear about it, especially if your ideas are very simple. Okay, so this is a paper, but actually one of the most popular papers in machine learning. It's about the ADAM optimizer, ADAM. That paper has been cited more than 50,000 times. This paper was rejected initially. It was never published. It's still in the archive. So people use that paper because the algorithm is very useful. It's very simple, but very useful. Algorithm, I will use ADAM a lot in here. So let me say, what is a PIN? What is a physics-informed neural network? And it's a very simple cartoon here. So let me start from the left. The left is a standard neural network. I already told you how to find a U. If you give X and T, position and time, and U of XT, the label data, this is supervised learning, then you learn these connections. These connections simply represent the weights and the biases. So the math behind it is very simple. It's down here. Is this mean square error, just like a least square error. The predictions of the neural network in every iteration have to be matched with the data that you're given. And if you have a lot of data, do many iterations, you find all these connections. Okay, you can be more fancy, you can use other networks and so on. You can have images, you can have hybrid data, low fidelity, multi-fidelity data, multimodality data. But the main idea is that from the data, you find the connections. However, as I said, we have dinky data. Not a lot of data, and some data is there. So what you have, however, is physics. For example, here, I pretend that I have this parameterized nonlinear Schrödinger equation in one dimension. I don't know if all the terms are there, so I parameterize with lambda 1, lambda 2. So I have some data on this side, and I have some physics on this side. Now, how do I deal with the physics? Well, I'm not going to use the standard methods that I teach in my class, spectral methods, finite elements, finite difference, finite volumes, all these type of methods. I'm going to use something different. In order to evaluate these operators, I will use something called automatic differentiation. Automatic differentiation is a very useful tool. It's different than symbolic differentiation that you may have heard in optimization. But it's part of all the frameworks now that the Google and PyTorch, TensorFlow, and so on. So basically, it allows you to do a differentiation of the network itself. U, a approximation of a solution U, is a neural network. So automatic differentiation allows you to take derivatives of the neural network itself, not of the data. That's very important because the data may be noisy. So this technology is used, in fact, when you try to minimize this function, what's called the loss function. They use objective function is loss function. When you try to minimize that and you take the partial derivatives with respect to the parameters, the weights, and the biases, this is how they use automatic differentiation. I use here automatic differentiation to approximate all my differential operators. Why is that important? Well, it is important because now I can do derivatives and higher derivatives without having a grid. I don't need an approximation to my numerical derivatives. X and T will be continuous, but more importantly, for engineering applications, imagine you are simulating a very complex object like a gearbox, like an airplane. I do not have to build a grid. And grid generation, mesh generation is a very expensive task in engineering in real applications or in moving domains. Imagine you have moving domains. So we remove the tyranny of the grids by doing this very simple automatic differentiation to represent the function. So as you now correspondingly, you can add to the loss function this term here, which relates to the physics. So F is the residual. So you're trying to minimize the residual, just like you try to minimize the misfit in the data. You can combine the two to now have a composite loss function. Now you can put weights in front and so on, that's technicality. But the most important thing is that if you have a lot of data, you can afford to have less physics. If you have a lot of physics, you can afford to have less data. So this is a seamless integration of forward problem and inverse problems. So you're interested in inverse problems, it means that you know much less physics and you have a lot of data. If you have a lot of physics, then you need less data. Now, after you reach this point, then you use our Adam optimizer, which I talked about, or after you converge with Adam, you can finish up to increase the accuracy with second order Newton, quasi-Newton methods and so on. But this is standard off-the-shelf optimizers. So this method now becomes very, very simple. We don't have to build grids. Any high school student can write the code. As you can see, the code is very simple. So the industry loves it. And I have a slide here to show you that the industry has really embraced this type of approach because it's a very, very simple approach and you can get results very quickly. The accuracy is not tremendous, like you have with spectral methods, for example, but you can get things done very quickly. The students like it because in one afternoon they can get results on any problems, literally. the national lab researchers like it because you can incorporate noisy data, uncertainties, and so on. And a lot of researchers like it because they can write papers, new papers to improve it. In fact, I just received a paper from a colleague whose student improved our method 11,000 times faster speed up. So I was very happy to say that, okay, our method is not so good, but your method, which is modification of our method, is much faster. So I encourage everyone to try it. Now, let me give you an example of how simple this is. We're looking at the Berger's equation. It's a PDE, has a second order derivatives. As you can see, it's kind of like a model for turbulence. Now, the domain is x and t. So as I said, I'm not going to discretize t, and I'm not going to discretize x. These are continuous variables. So avoid the artifacts of artificial dissipation or dispersion. So I have these points. These are my data points, my initial conditions, and I have boundary conditions. Now notice that in this region, I don't know the boundary conditions. Over this time interval, which is substantial, I don't have any information on boundary conditions. However, the method works without boundary conditions. We have theory that proves that. So these are my data, and we'll go into the first term that as I showed you before. Now we have the PDE, which will evaluate at random points inside the domain xt. So x and t is a space-time domain. I don't split space and time. I consider it the same. So I will take random points, evaluate this. So let's write the code together. We use TensorFlow. With one line here, TF stands, I define my neural network for data. Then I compute the residual f. First derivative in time, first derivative in x, second derivative in x. I add it up. I send to my optimizer. And 30 minutes later, I obtain my solutions, which, as you can see, are pretty good looking solution. No overshoots, no undershoots, no Gibbs oscillations, starting from scratch. But as I said, the method is very simple. It's about 10 lines of code that even professors now know how to program their own ideas. So that's very useful for me. So there's also flexibility. This is an example here where I have the same case, the Berger's equation, the xt domain. I now have two subdomains. One is my dolphin domain, and of course that's the blue sea. So I have two domains. I use domain decomposition in space-time. Very hard to decompose time and do parallel computation. But here I do a parallel computation in space-time. I use one neural network for the blue part, another one for the dolphin. Why do I do that? It's because I want to solve problems faster, twice as fast, because I will do it in parallel. Also, I may have multi-physics, multi-scale problems. I may have stiffness, and I may want to use different activation functions, different number of neurons, different numbers of points where we evaluate, and so on. So the connection here, unlike, you can see it's a very complicated domain. There's no domain decomposition in the world that can do that. Finite elements can not do that because you have non-convex domains. You cannot do mappings and so on. But what you can do here is you can put a lot of points on the boundary, and then you can penalize the residuals across. You know, the residual has to be 0, therefore it's continuous. You can penalize across the lines. And you can see here, down here, the solution is seamless from one domain to the other. You can get twice. Of course, if you break up into 10 domains, the speed up is 10 times and so on. So it gives you a huge flexibility. I have some other applications, how you can go to turbulence. The work that I've done with Johns Hopkins, laminar transition from laminar to turbulence. If you're interested, I can talk about it. I want to show you my coffee example. I don't know if you can see the movie, but what I show you here on the left is the picture of LaVision at the center plane. Then I match it. This is from the pin. I matched. And then in the process, what I do, because of the coupling of the passive scalar, I can also extract the pressure field and the velocity field. Now, another thing that we noticed was that we found that the maximum velocity over the cap was, this is, I don't know if you can see my cap here. It's this cap, it has a neural network on it, a pin. We found that the maximum velocity was 0.4 meters per second, which is too high. I didn't believe my own results. So the LaVision people in Göttingen went back and they said, they looked at the movies and they said, well, they guesstimate 0.08 meters per second, which I agree. But then one day they called me and they said they did a PIV independent experiment and they found that the maximum velocity is indeed 0.4 to 0.45 meters per second. second, okay? So that was really pleasing. But what we had in this question that I asked you earlier, can you find the forces on the body? So the neural network now looks a little complicated. Here's the data, here's all the velocities and the pressure, and here's the equation, passive scalar, the Navier-Stokes equations, the compressibility. All this can be done with automatic differentiation very quickly. So I challenged my postdocs and I said, if I give you a video of dye that is visualization right here in the arbitrary patch in this flower, without telling you what the Reynolds number is, without telling you the boundary conditions, the initial conditions, can you find the velocity and the pressure? And these plots here, you can look up a science paper, are there to show you that. Then we said, can you find the forces if the dye goes around the body? Because here we didn't even know that there was a body. One of our reviewers sent us this picture from the Van Dyke album of pictures of motion, from fluid motion. He said, can you do that? So we recreate this in a computer. We have strict lines for a cylinder and so on. And you can see here, we can predict the CL and the CD within a couple of percentage using just flow visualization. So that opens up a lot of different applications. For example, we work with the Coast Guard for rescue operations, for spill, oil spill problems and so on. So this is we're going now to Mexico, the Gulf of Mexico. There's a region here, it's called Laser. And we have data from satellites for the sea surface temperature. Given sea surface temperature from satellite images that you can use CNN to easily obtain it, can you infer the velocity field? Okay, obviously that's a nil-pose problem. Just make the connection, but here I can show you that these are the temperature images, and this is the estimate field. It takes about 0.1 second to infer the velocity field, the currents, just from temperature, because of the coupling, because of this hidden fluid mechanics. And we call it hidden fluid mechanics because it's like a hidden Markov process. You have data on auxiliary variables, but you don't have data on the primary variables, which is the velocity or the pressure and so on. Here we have an ocean model, which takes a day at least to run, compared to 0.1 second to infer the velocity field. Here's another picture from LaVision. We found that that's how we made a connection with industry. I love to work with industry. And I know Aachen is very big on that, and many German universities. So what they had here was our collaborator now, Thomas Berg, who is puffing without a mask and with a mask. And again, it's a Slirian photography, and we wanted to quantify the velocity field and also the pressure field. Here I just have a movie for the pressure field to show that just using these images, this 2D video, I can quantify the field with and without the mask here. You can see the puff, same puff when you have the mask, doesn't propagate. The velocity is 10 times smaller and so on. Here's a biomedical application. This is a real problem. This is some collaboration with the work from Children's Hospital. What you see here is an intracranial artery. There's a dilation that's called an aneurysm. This aneurysm is about to rupture. And the big, of course, nightmare is when will this aneurysm rupture? As engineers, we know that this will rupture if the pressure forces and the wall shear stress is big. But what the doctor has is this dye visualization, a contrasting agent, just like this, black and white. And the doctor with the naked eye says, okay, there is flow there, there's still growing. Maybe in a month we'll have to operate. It's a very empirical guess for something very, very critical. As you can see, this will lead to brain stroke. So we said, can you quantify this using hidden fluid mechanics? Indeed, just using the dye visualization, just like I show you, you can quantify the velocity field and the pressure field. This is all the images here inside the aneurysm. And based on that, you can compute the velocity field and from there, the wall shear stress and the pressure field. Here I show you that if you do a sort of a posteriori simulation with CFD, you get the velocity field very accurately in this very complicated vertical field. I'll go back now to the third. I think I show you three questions. The ill-posed problem in mechanics, hyperelastic solids. Where is the hole? How big it is? Now you have to dial in some different equations, constitutive equations. Not straightforward, but it's probably takes an hour, 2 hours to do all this. But if you have measurements like this, and these are very sparse measurements, I don't have any stress or strains, I only have displacements on these points. And I ask the question, where's the hole, how big it is, and so on. So here in this video, I want to show you that if I start with a totally wrong location of it's something that you cannot do with standard finite elements because the topology changes. You don't know where the hole is, and the deformations is huge. What all this shows you is that you can find, you parameterize the geometry as an ellipse. If it's not an ellipse, you can use NURBS to find all the coordinates and so on. But from data, you can find if you have, so this is non-destructive evaluation of materials. A real application is this one here that I want to show you. I don't know if you can see a video playing. Not moving. But let me just go back. Okay, here. Yeah, I think, Aravid, can you see the?
Yeah, it's moving.
Okay, it's moving. So there's this front of ultrasound that hits on the left. It hits a crack. It's a surface crack. Real data from the Air Force. This was a hackathon at DARPA. There were 12 teams. My team was the only one who finished the project. And the reason we finished the project is because we use physics. Most of the teams said they didn't have enough data. We use only 10% of the data. The reason is because we use the wave equation. We said, well, this is the wave equation. We make C variable. The wave speed is variable. You can see we have a neural network for the wave speed. If you quantify the wave speed as a function, not a constant, then you know where the crack is. On the right, you see we match the data we're given. As I said, we only use 10% of the data. Now, I want to also make this point that we use this application to advance the state of the art in neural networks. All neural networks now all neurons fire at the same rate. We said, why is that? In the brain, that doesn't happen. So we change the activation function to be an adaptive activation function. Every neuron will fire at its own rate. This will avoid bad minima in the optimization method. We have a theorem about it. We proved with some colleagues from MIT. So adaptive activation functions was introduced for this application. Now the community is using it everywhere for commercial machine learning applications. So I talked about lots of pins. We have many more. It's an alphabet, as I said, for high-speed flows, stochastic PDEs, fractional PDEs. I'm not going to cover all this because let me just check the time. Arvind, can you tell me how much time I have so I can?
More 20 minutes.
20 minutes. Okay, great. Let me just show you quickly for stochastic PDEs what we do, and then I will move on. For stochastic PDEs, we use these GANs, this generative adversarial network. Discriminator is a network that we're trying to train, but we don't have enough data. So these are the real data, but we also have a generator. And as you know, we are in an election year in the United States, looking forward to November 3rd. But a generator creates fake news, fake data, and then the discriminator has to also realize or discriminate against the fake data versus the real data. In this adversarial game, generator and discriminator are two players playing a game. They will come to sort of Nash equilibrium, and when the generator becomes better and better and smarter, the discriminator becomes better and better. Eventually, we'll train the discriminator with less data. So here we're talking about probabilistic inputs, because we start with some noise, stochastic inputs, and so on. So this is really a very important type of classes of neural networks, but we use it in a different context. Suppose you have this porous media equation. It's an elliptic equation, as you can see. I have a right-hand side, which is like the pressure, for example, for which we know a few data, and there's a lot of uncertainty. Omega denotes uncertainty. The hydraulic conductivity is for stochastic process, and I know some data. Then I have the velocity, and I know some data, but I don't have everywhere. So this is sort of a hybrid inverse forward problem. I know part of the solution, I know part of the right-hand side, I know part of the material. Okay, so we modify this GAN to include here into the data, we include all the green part is where the stochastic PDE goes. So now the discriminator has much more to work with We solved this in one of our papers. We solved this stochastic PD for a real application. The Hanford site, where all the nuclear waste of the United States is buried, and it has to be monitored with 1,000 wells, which will give you data here. We solved this in 10,000 dimensions using GANs. I will skip some of it because I want to tell you a real application. This is a very big movie, so I don't know, Aravid, can you tell me if this works?
Yes, we can see it.
What you see is a real destroyer going through the North Atlantic Sea State 8, which means waves of height of about 20 meters. Of course, we're interested in the digital twin of that. We're interested in autonomy. We want to know what is the sea keeping? What is the dynamic motion of this given a stochastic elevation of the sea? What you are watching is a movie that was made with OpenFOAM, and one of these simulations takes about 1 week to complete because you have free surfaces, you have an Navier-Stokes solver, you have viscosity effects, and you have fluid structure interactions with moving domains. It's a very expensive computation, 300 processors, about 1 week. Now, that's totally useless if you are interested in autonomy, because you have to decide how to navigate through this
Did we lose connection with George?
To predict the motion, the 6 degrees of freedom. Okay. Can you hear me now?
Yeah.
Okay. I know I lost connection, but basically we are trying to predict the motion of the destroyer using an excitation which is stochastic in nature. Okay. For every sea North Atlantic, we know the spectrum and so on. So here's the second theorem. So I was looking for theory. I wanted to start with theory. It says, can you approximate a functional? And if you read the web, in all the blogs, they don't really have the answer. They say, oh, yeah, it's cool. I did it, and sometimes it works, sometimes it doesn't work. Well, there's this theorem by Chen and Chen from Fudan University in China in the 90s, the same time as the Saipenko theorem, that says that, yes, you can approximate a functional using neural networks. U of x will be the function, and f of u will be the function. The output is also a functional. Okay, it's a functional. And you can do it in 1D, you can do it in 2D. So in fact, what we did, we use a standard neural networks, something that has memory. So we use as an input the stochastic excitation 1, 2, 3 times. We train the network with labeled data. So no physics here. Offline, we train this. It's a very painful exercise, but you do it offline, just like you train low-dimensional models. You can actually, we use as one of the networks, we use sequence to sequence, that is using natural language processing for Google in your iPhone. We use also an LSTM, a recurrent neural network. And guess what happened? We can now forecast the rolling, the heaving, the motion of this neural network for one excitation or another excitation. As you can see, the excitation is stochastic, the response is stochastic. In the background, you can see the CFD. It takes about 0.01 seconds, almost real time for autonomy for this application. So my point is, as you go from function approximation to a functional approximation, you gain in generalization, you gain in transfer learning, you gain in robustness. And that's very, very important for our applications, autonomy and otherwise. Now, how about general nonlinear operators? Because that's very important for collective intelligence, for true intelligence. True intelligence requires abstraction. Abstraction can be expressed with nonlinear operators, not just function approximation. So the question we pose now is, can we approximate nonlinear operators, arbitrary, continuous nonlinear operators? Is there a theory for it? Well, again, if I go to Chen and Chen, and Chen just emailed me a couple of days ago, he's 87 years old now, thanked me for putting the spotlight on his theorem. He proved this theorem for just one shallow network, one layer. But this neural network is different. So here's the setup. I take functions as input from a compact space V. G is the nonlinear continuous operator I'm trying to approximate. And then G of U of Y is the nonlinear operator. And the theorem says, having only a single neural network, you can approximate this input function. This is the input function. You can approximate the functional with epsilon accuracy. Epsilon can be arbitrarily close to 0. Now, here I have two neural networks. I have this one here, and I have this. This is the math. Chen never implemented this, never extended to a deep neural network, but in more recent work that will be published in Nature, our paper extended this to a deep neural network. So now you can see we have a trunk and we have a branch, but this could be an arbitrary neural network. In fact, it could be radial basis functions. It could be any complete approximation, nonlinear approximation, or can approximate a nonlinear operator. Now, that nonlinear operator could be a Laplace transform, a linear operator. It could be a PDE. It could be a system. And this, I wanted to present this to you, to this audience, because you have an interest in system identification. This is exactly for system identification, for tapping on this black box system with measurements and discover this system. This is sort of a nonlinear transfer function, if you like. It's a mapping from a functional space to a functional space. And that's the nonlinear mapping. So this is what I show here schematically. U is an input, could be a vector of many functions. The G of U is an output. So you give me one function and you give me observations of G of U. You give me another function observations. In fact, let's go to panel B down here. Panel B, I observe the function on a few points. I observe the output on only a very few points. And I keep doing that for 10,000 functions. Eventually, I discover this operator G. After I discover the operator, then I can do lots of things with that, lots of applications, a surrogate in design optimization, or real-time predictions in autonomous systems. Now, how do you implement this? And this is the paper I mentioned, that we have 16 different applications of this neural network. But the way to implement this is with this branch and trunk neural network. So this is a composite neural network. They input this parenthesis here. So this is an example of how you can take math and make it real useful. Take this big parenthesis and make it a neural network. That's the branch neural network, which will be evaluated, eventually will be a cross product with the output. And you can see the output space is also a neural network because it's a functional, right? It's a functional space. So sigma is one activation function on the input. Sigma is another activation function on the output. Then you take the cross product and you have G of U of Y. I'm going to demonstrate this on a very, very simple problem. And that is, can I use a neural network to approximate the integral? So I don't have to do all these integrations. I remember this formula, so I use Mathematica for that reason. Okay, so I take a function, an integrand, U of t, and I want to obtain the integral S of x. X is, of course, in the range from 0 to 1, could be from 0 to 100. And how do I do that? Well, I will take 10,000 integrands. I have to define a space. My space here is a Gauss random field. I have a Gauss kernel, Gaussian kernel, and I pull functions for a given correlation length. And I observe it. You can see I only observe the output at one point, S of x. For that one function, I only observe at one point, not at many points, although x is between 0 and 1. And I have an infinite number of points to observe it. I only observe it at one point. And I can train this network. This is the mean square error versus number of iterations. I can test now my operator for unseen data. And you can see the training error, the testing error is the same, which means generalization, which is the holy grail in neural networks, is what's the generalization error? If I train the network and you give me new data, new functions, in fact, how well you're doing. And you can see here, the neural network we design compared to other neural networks, the feed forward and other sequence to sequence, we use the Google neural network, it's not good enough. You can see that I learned really quickly, and I also have a very small generalization error, the difference between the red and the blue. Can you do that for real applications? I have, as I said, 16 different examples for stochastic PDEs, fractional, and so on, but here I want to show you real applications. This is of microbubbles. There's an equation here that will generate bubbles, relates to the radius as a function of time, given some pressure difference. So I use the equation to generate data. Now, if I work with an experimentalist, and I love experimentalists, I work for data these days, not for money. I love data. I will take the input, the pressure difference, which is used to measure, and with a video you can have R, So, but here I just use synthetic data using this Rayleigh-Placet equation. So my input will be a function of time. My output will be a function of time. The input goes to here, the branch. The output will be the trunk. And you can see here for arbitrary pressure distributions, I can learn how this bubble oscillates, how it grows, how it decays. And this is now prediction, which means unseen data. I test it for pressure differences that I have not seen before. You can do that for nanobubbles using molecular dynamics simulation. You can even capture the thermal fluctuations, you can see. You can do it for shocks. You can learn, you can use DeepONet to learn the Euler equations with chemistry, which is a very difficult problem. As you can see here. So these are three species with so specifically what we do here, we have generate data. So my input function will be the initial conditions, the initial Riemann problem that you set up. So that will depend on the discontinuity, how smooth it is. And I have eta as a parameter. So I can make smooth initial conditions, very steep initial conditions, and I get a multitude of solutions, of course. So that's my input space. And then I train networks, building blocks. This is a Lego that I talked about. DeepONet will give me nitrogen, oxygen, O, U, and T. Okay, so I have now building blocks for operators, which represent the entire PDE, the set of conservation laws. Now, after I train it, and you can see I only use 100 trajectories to train it in time. So you can see I use then 50 to test it. But this is one case. I start with a black line, which is initial condition. It's not very steep, as you can see, but eventually, because the Euler equations, you develop shocks at different locations for different species. And I can predict in 10 to the minus 5, and I can predict 10,000 times faster than the CFD solver, because this is 0.01 second to do the prediction. So having this now, and this is my last example, I can build something really exciting. I can use DeepONet for hypersonics, which is very, very hot topic, as you know right now. Now, for good reason, the research is incomplete. There are not many wind tunnels right now that can do this experiment, so we have to rely on measurements and very few measurements. So, but this is a full system of Navier-Stokes equations, and in this particular case, I will be looking downstream of the shock, Mach number between 8 and 10. In that Mach number range, we have the nitrogen, the oxygen will dissociate. We have 5 species now to keep track of. The chemistry creates extremely strict conditions on the time step. So CFD solvers are very expensive. So we want to replace them with offline training of these DeepONets. So I will have temperature and velocity as an input, and I can predict chemistry. Okay, so I use some data to train it, but basically I will have these building blocks. Or the opposite, I can have the chemistry. If you give me the chemistry, I can predict the velocity and the temperature. And here I show you the example of the data I use. The data is very strange. You can see here, for example, density of N varies over 8 orders of magnitude, 10 to the minus 8 to order 1. And this Mach number range. I can predict very accurately. If you give me the velocity and temperature, I can predict the chemistry here very, very accurately. And the opposite. Now, what happens in flight, on the flight, literally? This is where DeepMNM comes in, the multi-physics and multi-scale. So I take all these building blocks, and I assume that in the flight, you don't have measurements of chemistry. It's very difficult. But you may have some chemistry, some data on velocity and temperature from instruments that you have, infrared cameras for temperature and so on, thermocouples, and some velocity measurements. You can have pressure also. So you assume that you have, so you set up this DeepMNM, an umbrella neural network. These are my building blocks. I can predict, given velocity and temperature, as I told you, I can predict all this chemistry. Given the chemistry, because I have a bidirectional coupling, I can have new velocities and temperatures. Now I have to compare these velocities and temperatures with the real data. So I set up a loss function where I compare the operators, are the operators right, are the data, so I match the data in one regularization term. So that's a DeepMNM. I can build an arbitrary multi-physics system using offline data. Here, as you can see, I use this pink data, very few data on the velocity and temperature. I can get the species everywhere very accurately. The important thing is this is 1D example, only in X, and I am 50,000 times faster than the CFD solver. And the accuracy is pretty respectable, 10 to the minus 5 accuracy. Now, so far I sounded very euphoric, very happy, very satisfied, but I want to give you a warning. So in ending my presentation, I want to fire a warning shot. And that is basically that math is important. I told you all the great things that we can do. And there's a lot of hype. And my presentation was supposed to be very optimistic, but I want to also give this warning. So I asked one of my students to approximate this function, f of x is absolute value of x. Now, according to universal function approximation, that should be no-brainer. In fact, if you use the ReLU function, like the RAM function to the right, RAM function to the left, you can approximate this function exactly with only 2 layers and 2 neurons. No problem. Okay, so let's take a 10-layer neural network with 2, and let's try to train it. What will we get? Well, the absolute value of x is this, the blue line. 93% of the times we'll get this dotted line. 7% will get part of the branch right, and we'll get this. This is sort of the average value. So what happens is the approximation error is 0, not epsilon, 0. However, we fail to learn this function because there's a huge error that's called the optimization error. In fact, when you analyze the error in neural networks, this is a neural network. This is the approximation error. This is the true solution. How far is the neural network from the true solution? As I make this box bigger, I make my neural network bigger and deeper and wider, I go closer to this. But notice here, I still have the generalization error, which means I sample my space very sparsely. I replace an integral with a sum. And here's the optimization error. The holy grail in machine learning, and that's what you all young guys should tackle, is the fact that we have to solve minimization problem of a high dimensional non-convex function. Well, there's no theory for that. And many times we may latch on the wrong minimum. So we may get the wrong answer, just like in this function. Imagine you do a multi-physics problem with unknown outcomes for a real application, and you have to put certificates of fidelity for your product, for this engineering product. That will be a disaster. Optimization error is very big. There's no guarantee. It's a global optimization. There's no guarantee. The function we try to optimize, to minimize, is we use stochastic gradients. Sometimes they work, sometimes they don't work. On the positive side is that physics that we use regularizes this very rough landscape of a loss function. So it minimizes the number of minima we have to detect. It smooths in some way this rough landscape. Imagine you are, the loss function is like the Alps, and there's lots of peaks, lots of valleys. What's the right one for this problem, this nonlinear problem? I want to give you with that. So mathematics is still very important, and I see that as the next frontier. Various aspects, multi-fidelity approximation I talked about, and nonlinear approximation. We are in the beginning of what will develop in the next 10 years, I think, in this field. One of the big questions is how do you know that you learn? You have only small data and some physics. So this is optimization in the manifold. It's not like what people do in commercial machine learning, where they don't need very much accuracy to say if you give you a recommending system for this type of shoes or another type of shoes, or this type of wines or different type of wines. Let me also give this, I'm done, Ravind, that this paper here, and this DeepXD is a software we put on the web. You can download it. In fact, as of September, we had 56,000 downloads. DeepXD solves any differential equation for X. It's mostly for educational purposes. It has some simple modules of geometry and so on, but X stands for anything. PD, and ODE, stochastic and fractional and so on. So it's a very good tool to start with. It's written in Python and TensorFlow. I also want to give you this advertisement. This is Films is the best, not the best, it's the first big center that on physics informed learning. Again, we wrote the proposal 5 years ago. It was rejected many times. Eventually, the Department of Energy picked it up. I'm the director. We have good people from MIT, from Sandia, from Stanford, Santa Barbara, and we hire lots of postdocs in this center. It's a multi-million-dollar operation. We have many positions for this type of work. So if you are interested in learning about these things, this is a good place to and you can work with any of these partners. We also started with also good people, this MURI, this multi-university research initiative. This is like the centers of excellence that you have in Germany that these are excellent ways of not just promoting science, but also training young scientists to be the next generation of great computational scientists. So our partners here is Caltech and Stanford and the University of Utah. I'm the director, and the focus is on mathematics of machine learning, and the applications is non-destructive evaluation of materials and hypersonics and so on. So with that, I would like to thank you very much for your attention. I'm sorry I went a little over the limit, but lots to cover, lots of topics. Thank you very much.